This presentation provides an overview of Chapter 10 in the book titled, Simple G, a gridded economic approach to analysis of sustainability of the Earth's land and water resources, edited by Iman Hakiki and Thomas Hurdle, and published by Springer. This chapter covers the R&D cost of climate mitigation in agriculture. Agriculture is a major source of greenhouse gas emissions. Land use change, livestock production, rice growing, use of fertilizer, and other agricultural activities all produce greenhouse gases, contributing to global warming. By raising agricultural productivity, though, it might be possible to reduce the resources employed in agriculture, and therefore, reduce greenhouse gas emissions from the sector. This chapter uses the simple model to investigate these questions. This slide provides an overview of all chapters in the Simple G book, each of which has an accompanying presentation to motivate the material covered in that chapter. During this presentation, I'll cover Chapter 10, which is on the R&D cost of climate mitigation in agriculture. Previous chapters laid the groundwork by providing theoretical foundations, introducing general conditions, specifying mathematical equations, discussing the gridded data and parameters, and computer implementation and validation. In this first applications chapter, we'll focus on implementation of the non-gridded version of the model. This chapter uses the simple model to investigate how investment in research and development, or R&D, can accelerate productivity growth in agriculture, thereby helping to reduce greenhouse gas emissions, and therefore, mitigate climate change. This application involves incorporating shocks to total factor productivity, or TFP, in the simple model, and examining how this affects equilibrium output, prices, resource use, and GHG emissions. The application also requires a framework for linking R&D investment to productivity growth in order to derive the policy cost of this approach to GHG emissions abatement. Evidence shows that greenhouse gas emissions vary widely across the globe. Emissions intensity, or the emissions per unit of agricultural output, has also fallen significantly over the past few decades. This is because productivity growth has both slowed the rate of land use change and improved the efficiency with which resources are used to produce agricultural commodities. Variation in agricultural emissions and emissions intensity is also affected by the commodity mix. Regions with large numbers of ruminant livestock, like Oceania and Sub-Saharan Africa, or large areas in rice production, like Southeast Asia, may have relatively large emissions intensities, especially if commodity yield is low. Land use change also produces large amounts of emissions, and productivity can reduce incentives to expand land into forests and natural grasslands. Land use change is also affected by national environmental policies, such as policies that protect carbon-rich lands from agriculture or other uses. Deriving productivity growth from R&D investment requires two steps. First, we must assume an R&D capital structure. Using this structure, we estimate the stock of R&D, or knowledge capital that accumulates from a stream of annual investments in R&D. We need to take into account the fact that there is often a gestation period between when R&D investment is made and when that research results in new technology that is widely adopted by producers. It may take a decade or more for a research investment to have its full impact on productivity. We should also consider that R&D capital, like physical capital, will eventually depreciate through technological obsolescence. In this figure, we show two common capital structures. The dashed line shows the typical capital structure for an investment in physical capital, like a new tractor. In year 1, when the tractor is new, its productivity is highest. For example, $1 of physical capital investment adds $1 to physical capital stock. Over time, the capital item becomes less productive due to wear and tear, and after say 15 years, the capital item will be discarded. The solid line shows a typical capital structure for R&D investment. $1 of R&D investment in time zero will add $1 to R&D capital stock, only when the technology is developed and adopted by its fullest extent by farmers, perhaps 10 or 20 years after the initial R&D investment. That investment, however, will continue to contribute to productivity for several more decades before it is completely depreciated. The second step in linking R&D investments to productivity is to specify values of R&D elasticities, which give the percentage change in TFP for every 1% change in R&D capital stock. Many econometric studies have estimated agricultural R&D elasticities for different countries of the world, using historical data on public and private R&D spending, and how it affects growth in agricultural TFP. In Chapter 10, we specify 5 scenarios for global agricultural R&D spending over the 2017 to 2050 period. The first scenario is the business-as-usual case, where we assume that R&D spending in various global regions continues to grow at the same rate as the last couple of decades. In Scenario 2, we assume R&D spending accelerates, which leads to faster growth in R&D capital stock and TFP. Incorporating the technology shocks from R&D spending into simple and solving for a new market equilibrium shows how this affects prices and how producers and consumers respond to changing conditions. Faster TFP growth reduces commodity prices and causes agricultural land area to contract globally, reducing GHG emissions. Scenario 3 assumes an environmental policy that pays owners of carbon-rich lands, such as forests and peatlands, to preserve these areas in their natural state. The payment compensates landowners for foregone income from not cultivating them. This also reduces land use change and emissions, but the new simple solution shows that agricultural prices rise as supply is restricted. Furthermore, payments need to be maintained in perpetuity. Scenario 4 combines more R&D spending in developing countries with environmental policies to preserve the most carbon-rich lands from agricultural uses. Scenario 5 shifts some of the increase in R&D spending from developing to developed countries, taking advantage of the higher returns to R&D spending in developed countries, as indicated by econometric estimates of R&D elasticities, especially since R&D in developed countries has been shown to generate more international knowledge and technology spillovers. Climate abatement strategies that cost less than $100 per ton of CO2 equivalent are generally considered to be cost-effective. According to the results of this application, agricultural R&D appears to be a low-cost strategy for climate mitigation. The marginal abatement cost of agricultural GHG emissions from more agricultural R&D spending in developing countries was estimated to be about $20 per ton, and only about $14 per ton if R&D spending also increased in developed countries. An important advantage of R&D spending versus land set-aside payments is that R&D spending lowers commodity prices, making food more affordable. Policies that restrict agricultural land expansion without compensating with higher productivity on existing agricultural land leads to higher commodity prices and can exacerbate global food insecurity. On this slide, you'll find the link to the Simple G webpage where you can find additional resources, as well as links to the book and other chapter presentations. Lastly, we also gratefully acknowledge support from the U.S. Department of Energy, the Department of Agriculture, and the National Science Foundation. Thank you for watching this presentation on the Simple G book, Chapter 10. We encourage you to explore the other companion videos that accompany the book on the Simple G webpage.